So you are given an undirected graph tree with n nodes, which is numbered from 0 to n minus 1. So undirected weight means, what is the meaning? So undirected weighted tree means there is no direction, like from A node to B it is not given, and weighted means there. So if we are connecting one nodes to another nodes, there will be weight, right? Means some value will be given. Let's suppose, for example, so there is an edge from node U to node V, and for this node to node U to node V, there is a connection, and for that connection the weight is given like this. Okay, means we have given an undirected weighted graph, or you can say tree with n nodes, which is numbered from 0 to n minus 1. It means if the nodes are n, right? If there is n nodes are given and you are doing 0 to n minus 1, means this is a acyclic graph, right? So it is represented by a 2D integer array is of length n minus 1, where the edges we have given like this, like the node A, node B, and the connection for this, the weight of each index we have given, right? So each index will contain three things: U, V, and W. So what does it mean, right? So it indicates that there is an edge between node Ui and Vi with the weight Wi, right? So if there is two nodes U and V and it's connecting with the weight Wi. So additionally, you are given 2D integers array queries, where queries at J means source, from source 1, source 2, there will be destination, right? So we have to return the answer of length equal to the queries dot length, where answer at J is the minimum total weight of the subtree, such that it is possible to reach destination from both source 1 and source 2 using the edge in this subtree. And subtree, there is any connected subset of nodes edges of the original tree, forming a valid tree. Means what we have given, we have given a weighted undirected tree, and there is multiple queries we have given. So each query contains three things: source 1, source 2, and the destination, right? And you need to find the minimum total weight of a subtree, such that like source 1 and source 2 can reach the destination using the paths in the subtree, right, that we have given. Okay, so what is our goal? So for each queries, right, for each queries that we have given in this array, we have to return the minimum total weight of subtree that allows both source 1 and source 2 to reach the destination. Okay, and so if you talk about the intuition, what is the intuition? So in a tree, there is only one unique path, right, between any two nodes, right? If we talk about source, let's suppose if there is two nodes, node 1 and node 2, right? So there, from the node 1 to node 2, right, if we'll make a path, right, there will be only one unique path, right? So to find the smallest subtree, right, connecting three nodes, let's suppose, so for two nodes there is only path, right? And to find the smallest subtree connecting with the three nodes, if there is three nodes, right? So if you are going to find the smallest subtree that connect the you can say these nodes, right, we need to compute the union of path. Let's suppose from source 1 to destination, right, source 2 to destination, again from source 1 to source 2, right? Means three, first from here, then here, and then here to here, right? Means almost we have to find the we need to compute the unique union of paths, right? So the total path is 3, and you have to find all those paths. So what we have given an undirected weighted graph first, and there is no cycle, because this is number from 0 to n minus 1 of the n nodes. So if n nodes are given from 0 to n minus 1, means this is a no cycle in this graph, right? So because there is n minus 1 exactly edges for the n nodes, right, as you can see. So it represented a 2D integer array, edges of length n minus 1. So if the edges is n minus 1, exactly n minus 1 edges for n nodes, right, it means there is no cycle, first of all. So for each query, right, that will gives us three nodes, right, source 1, source 2, and the destination, right? And what is our task? So for each query, we have to return the minimum weight of a subtree that lets both source 1 and source 2 to reach here, right? So let's suppose we have a tree with nodes that source 1 and source 2 and destination we will have given, and we have to find the unique path between them, right? And then we'll do exactly the question is saying. Okay, so so there is a trick, right, that we will understand. So the trick is here, like let's suppose in a tree, right, there is a smallest subtree connecting the three nodes, right, a b c d, that we are talking about, right? So if the a b and c, if we will mark, right, so in a tree the smallest subtree that connects the three nodes a b c is basically the union of a b, b c and AC, right? Means source means we can say the path between source 1 to source 2, right? Then from source 2 to destination, right? And from source 1 to destination, right? Means AB, BC and AC, right? Like that we have given, right? So how do we compute the weight of the subtree, right? So we will use the you can say tree metric, right? There is a tree metric concept. So in the tree metric concept, what we have to do actually, we have to compute the distance between A and B, means from source 1 to source 2. If you assume this is A, this is B and this is C, right? So distance, we have to calculate the distance between these two. Then you have to calculate the distance between these two, and then you have to calculate the distance between these three, right? All you have to do plus all the distance, all these three distance you have to do plus, means distance from AB, distance from BC plus distance plus AC, and then you have to divide, and that will come, that will be your tree metric, right? So you have to find the tree metric. Okay, so we'll we will divide by 2, and because the common edge between the path get counted twice, right? So let's suppose there is a common path, right? Why we are doing the we are finding the you can say distance, and then we are dividing, because uh, we used to divide by 2 because common edges will be between there, right? So between the path we will get counted twice, so we should not count twice, right? And so that we have to divide by 2. Okay, so let's understand the queries, right? So what we have given, we have given an undirected weight of n nodes, number from 0 to n minus 1, the tree described by an edge list like this. Okay, and this means there is an edge between nodes ui and nodes vi with the given weights. Okay, so there will be input, right? Input 1 is the tree structure. Let's suppose edges. So today integer array we have given, so there will be 3 elements of n minus 1 size that represent the n minus 1 edges in the tree, and each edges connect two nodes with a given weight. So you have to consider like this, so you can find exactly time complexity and space complexity. Okay, so you know the how many elements are given. So at each index 3 element was there, right? And for 3 elements, how many, what is the size of the array, the edge array? N minus 1. So you have to multiply it. Okay, then it also represents the n minus 1 edges in the tree. Means if you talk about this, right, it represent the n minus 1 edges in the tree, right? And the each edge connect two nodes with a given weights. That is clear. Now we have input 2, that is query. Queries, we have source 1, source 2 and destination. So each query task each query asks for information related to the three nodes, the source first node, second node and the destination node, right? So what is our goal? We have to process each query using the tree structure and the weight to drive the required insights. Okay, so let's assume that these are the edges we have given, right? Like this is the edges we have given. So these are the nodes 0 to 1, and this is weight 1 2 3, like that. And you can assume this from, let's suppose 0 to 1 we have given 4, so you can see 4, right? Then we have given 1 to 2, we have given 2, so you can say 2, right? So from 1 to 3 we have given some weight. Like this, some queries we have given and some edges we have given. Okay, so 2 inputs is there, some edges we have given, some queries we have given. Okay, so from queries we will for each queries, right, we will use this tree structure and the weight, and we'll find the you can say the data that we need to do. Okay, so let's understand example first. So in example 1 we have given these edges. So if you talk about this, you will get these edges, and we have given these queries. So from 2 to 3 is 4, and 0 to 4 is 5, right? So you have to calculate this. So how you're going to calculate this, let's understand. So the blue edges represents one of the subtree that yield the optimal answer, right? So answer at 0 means the total weight of the selected subtree ensure a path from source 1 is equal to 2, source 2 is 3 to the destination 4. and if we'll do plus 3 plus 5 plus 4, it will come what? 9 and 3 is 12, total 12. And if you do answer at 1, the total weight of the selected subtree inside the path. So it is source 1 is 0, source 2 is 2, destination is 5, build 2 plus 3 plus 6 is 11, right? So that is why we are getting 12 and 11. Okay, so you pause this video and go through this statement, you will understand. Okay, this is another example. You can pause this and you can understand. So for this small input, we have given the queries we have given. So it is saying that why we are getting 15, because if you talk about the source 1 is 0, source 2 is what, at 1, let's suppose, right? So if we'll this is source 1 and this is source 2 and this is destination, right, is 2. So if we'll do the plus, right, so this is 8 and this is 7, right? If we'll do the plus, it is coming 15. We have to return the 15. So what we have given? We have given the weighted undirected tree, that is a cyclic graph with n nodes, n minus 1 edges. We have multiple queries we have given, and for each query we need to find the minimum total weight of the subtree, right? From source 1 you can reach the destination, from source 2 you can reach the destination. So in a tree, unique path will be from source 1 to destination, and from source 2 to destination, and the source 1 to source 2, right? It all lies within the union of the path between the 3 nodes. So you have to find the minimum subtree connecting with the union we will find, like this we will find that. Okay, means if we'll talk about A, B and C, there is one path here, there is one path here, there is another path from here to here. Okay, so let's suppose the subtree will include those paths are source 1 to destination, source 2 to destination, right, which form a connected subtree. Like from, let's suppose from source 1 we have a common node, right, and there is a source 2 where it will connect here, right? Means we have to take the LCA of source 1 and source 2 and the destination, right? So the total weight will be, we have to take the destination distance of A and B, then distance of B and C, and then we have to do you can take minus also, distance at A and C, right? A and B, right? If you do divide, it is exactly equal to AB, BC, AC and BC by 2. Either you take this one or this one, the total weight will be this. Okay, what is LCA that we are talking about? We have the connected component subtree. Let's suppose for the 2 nodes, we have one node here, one node here, so there will be a common node, right? So this will be our common node is nothing but the LCA of the source 1 and source 2 and the destination, right? So what is LCA? So let's suppose in a tree, LCA of 2 nodes, let's suppose U and V, the lowest is the deepest one node in the tree, and there is an ancestor of both U and V. So for example, this is an example. So from, let's suppose, 3 and 4, if we will take the LCA of 3 and 4, it will come 1, right? Because 1 is the lowest node, that is an ancestor of both 3 and 4. If you will talk about the LCA of 3 and 4, 3 and 2, right? So 3 and 2 having the you can say ancestor is 0, right? So both will work like this. Okay, so you pause this video, understand the LCA and the lowest common ancestor. Okay, so you will not have the further understanding issue. Okay, why LCA is used? So in this problem we need to compute distance between nodes in a weighted tree. So the LCA is crucial for let's suppose there is a distance between 2 nodes U and V we have given, right? So we have to calculate the weight at U, weight at V, minus 2 into weight from root. Then that time we have to find the LCA of U and V, and you have to multiply it. Then you have to take the LCA of U and V. There will be some node, right? And that node weight we will multiply with 2, and you have to do minus, right? Either you will do the another formula that we have given, right? That we do either use this formula or this formula. Okay. So we have to update the formula. So this formula subtract the overlapping path portion from the root to the LCA once it is counted twice, right? Otherwise, how is LCA computed in the code? So we will use a technique called binary lifting, and so that we will compute 2 to the power jth parent for every nodes. So why we are going to use? So if we'll do the lift both nodes to the same depth, then lift them together until their parent match, right? We have to do lifting, right, up. So it will take of n log times for the LCA query. First of all, we'll take a variable log, 17. We'll take the log for binary lifting, and it is we will use for the LCA compute, right? And we have to check the, you can say, constant that we have given. So let me, as you can see, right, we have given that nodes are given what, n is greater than 3 and less than equal to 10 to the 5, right? So for that we have to to cover all the nodes, right, all nodes depth, right, we have to assume 2 to the power 17, and for that we will take the log 17. Okay, I hope you understand, right? Similarly, we'll create the graph. The graph will take a array of list of arrays, right, where we'll take all the nodes, right? Let's suppose a, b, and its weight will keep here, and all the adjacency nodes will come here. Okay, so for each graph nodes, or you can say adjacency list of the tree, where each edge has a neighbor and its weight, that will come into the graph, right? So we'll create a graph for the adjacency list, then we'll take the parent for binary lifting, and then we'll take the depth, right? So depth we will use to track the levels, which level we are currently. Then we'll take the weight from the root, right? We'll take the weight from the root, and so from the weight we use this weight from root to store cumulative distances. Okay, now understand the node, right? So we actually we can scan through edges and query to find the max node number, and that gives us n, the n number of nodes. Then we will build the graph using the adjacency list that we will do. Okay, after that we have to do DFS and binary lifting. So to understand that, we have given the minimum weight, right, and we have to find using the edges and the queries, right? This is our standard main function, right? So first of all, we will find the number of nodes from input and edges and the queries, right? So how we are going to find the number of edges, or you can say number of nodes? So we will scan through the edges and the query, and we'll find the max node number, and this will give you the n, right? As you can see, we will traverse all the edges, we'll find the n, right? We are finding the edge like this, and similarly from the queries we will find this, right? So you have to scan the edges and the query like this, and you have to find the max node number that will give that will give you n, the number of nodes in the graph, right? Then we will build the graph using the adjacency list, right? And to do that, let's go and build a undirected graph. So directed graph we have given, right? So we will build that, and so what we need to do, first of all, we will initialize the graph, right? And for all the nodes, we will initialize the graph at index, so that we will not get the null pointer, and we will initialize graph at I is equal to new array list, right? And after that, we will go through all the edges, and we'll add the two nodes value. We'll add the from each edge we'll get the e as an array of elements. So let's suppose for node 1 we have two things, node 1, node 2, right? From node 1 we will add what, node 2. So this is our neighbor node, and this will be our weight, the connection weight, you can say is weight, right? Similarly, we'll do for this one, we will do the reverse because it's undirected, so you have to do for E1. Means if A and B are two nodes, so first we have to mark A, that A have a neighbor B. Similarly, we have to do B have a neighbor A, means that we will do here, right? You know this, I think you're aware of this, like how the adjacency list works, right? Now we now start pre-processing, like we will use a root node, right? We will use a root node at node 0. We can say we root the tree at node 0, and we'll do DFS set. So what we need to do, some of the things we have to set. So if the root tree at node 0, we have to pre-compute parent, depth, and weight root. So we will set these values initially. So depth at node we'll do we have to set, then we have weight from the root, we have to set the node, and the parent at node and 0 we will say immediate parent, right? So this is our immediate parent, by default we'll say nothing is it is a 0, and depth at some value, like depth at node, we have to do. So we will initialize this and then we'll add it here. Okay, then what we need to do, we will fill the rest of the parent node using the binary lifting. How we are going to do binary lifting? So we'll do by we'll go through all the nodes, you can say, and we'll check its parent not equal to -1. Then we'll do the lifting, right? We will update our parent, and if there's no parent, we'll do -1. Next we will find you can say this is our main query where we will use the tree metric that we are talking about. So we'll compute the function like this is the standard function. If there is 3 nodes a, b, c are the points in the tree, so the smallest subtree covering them has a weight. For that we will do a distance between a and b plus distance of b and c and the distance of a and c, and we'll divide by 2. So we can discard the duplicacy, right? Twice that we are doing, that will discard. And then we will find the res. How we are going to find the res? We have to compute this function and we have to return it, right? So we are doing tree metric and we are find the res. Now as you know, I told you we will fill the parent nodes using these that we have defined here, right? So we'll use the parent nodes, right? Root node, right? And we'll define. So root node will fills the parent at node, and 0 will fills, and then weight we will fills, root node depth will fills, all we will fills. We will actually we are at the tree nodes, right? You can say root node, and that is why we have to set for the DFS, right? We will not set this, that we cannot call the DFS. Okay, so how we are going to set the DFS? Like this. So initially let's suppose it is 0, and this is par, and this is d, and this is current weight, right? So we'll provide all this, we will initialize, and we will traverse all the nodes, and internally we will traverse all the neighbor nodes. Okay, next is we'll find the next like this from the neighbor nodes, and we'll go to the next. Now it's time to understand the, we can say, this LC formula. I think you are aware of how to find the lowest common ancestor. You can do, there is a one Leetcode problem, you can do that, and you will understand the LCA. So LCA, we will take 2 nodes, right, and we'll check the depth, right? If depth at u is less than depth of this, so we'll take temp and we'll assign u, then we will do the assign of u is v. Now v is temp, means we are doing swap, so we'll do the swap. Similarly we'll uplift this, and then if this is the case, we'll return u. Any of them you can return, otherwise you can do the, you can find the uplifting here again, right? Means actually what we are doing here in the LCA function, we bring both nodes to the same depth, then we'll climb up until both meets, right? So we are doing, once we will match both, right, we will return that. Otherwise we'll do you can say climbing up until both meet, right? That we will doing here. Okay, I hope you understand, right? And finally we'll compute the distance, right? So to compute the distance, we have to use both u and v. You find the LCA node, and you can write the formula, right? This formula, and this formula will give you the distance, right? Distance. Okay, means we will take distance at u and v. We'll calculate this weight from root u of the node u from the root. Okay, like that. Okay, similarly. So if you understand this problem, right? If you understand this problem, so what we have done, right? So let's talk about the summary. So first of all, we'll define these variables, right? Then to find the minimum weights, we have to compute our, we have to find the n, means number of nodes. Then we will build the undirected graph, and after that we'll do the DFS. To do the DFS, we have to initialize that these values should be at the root. The code, let's summarize the code, right? So what was our goal? So first of all, our goal was for every query with nodes, we have three nodes was given, source 1, source 2, and the destination, right? And we have to find the minimum total weight of the subtree that connect all the 3 nodes in a tree, right? So if you talk about the intention, right? So in a tree, the minimum subtree contains 3 nodes a, b, c, has a weight. So we have to calculate the formula, right? What was the formula? As you remember, we have written somewhere, give me 1 second. So this was our formula, right? So we were using the tree metric identity and we were finding the formula, right? So means I'm trying to say, so in a tree, the minimal subtree containing three nodes ABC has weight and distance. How we are going to find the distance? So distance between AB, BC and AC we have to do find, and then we have to divide by 2, right? Like that. Okay. So in the first step we have to define the number of nodes, right? So we have defined the, but we have to find the, we have to determine the number of nodes. For that we have to initialize these things and we have to find the number of nodes, right? To determine the number of nodes we have to scan everything, right? We have to parse all the edges and the queries to find the maximum nodes index plus 1, and this will give you the total number of nodes. In step 2 what we will do, we'll build the undirected weighted graph, right? And we will use the adjacency list graph at node equal to the list of neighbor and the weight, right? We'll keep doing that and we'll add each edge in both direction since it is an undirected graph. So we'll keep doing that, right? What we will do, we'll add each edge in both direction, right? So that we will do here. Okay. In the step 3 what we should do, we will pre-process the tree data using the DFS, right? So we'll create a DFS function, right? As you can see here, we'll do DFS and we'll start from the node 0 and it will treat as a root, you can say. And for each node we have to record depth at node from the root, weight from the root node, and total weight from the root to this node. So parent at node and 0 means it is immediate parent that is used for binary lifting, right? That we will do these things, will do. So we have to initialize, initialize here means to pre-compute the parent depth and binary depth. We have to initialize this, right? And we have to do the DFS from here. We have to initialize this, and so the DFS method will call directly here. It means we will start from the DFS from the 0 nodes and it will move to all its you can say neighbor nodes, right? After that we will set up the binary lifting, right? To do the binary lifting we have to define what we'll use the dynamic programming to fill the parent, right? Like this we will do. And once this is done we will also enable the LCA function. As you can see here, we will define the LCA helper function. So when we are doing a DFS, right? So DFS will reverse the function to populate depth, then the parent, and then the weight from the root, right? Those things it will do. And when we are taking the LCA UV, it will compute the lowest common ancestor of two nodes using the binary lifting. Means if the distance at U and V, we have to compute the weight distance between U and V, and for that there is a formula that we will use, right? That is, what is this formula? This is the formula. So we will create a distance function to compute the weight between you can say U and V, right? So to find the weighted distance from U and V, between U and V, we have to use this formula, right? Means we have to compute the weighted distance between U and V, right? And we have to process each query. Let's suppose for each query there is a 3 distance U and V, right? So we have to find the distance between A and B and those, right? We have to do that, and we have to find each distance. Means we have to process each query, right? As you can see, we have to find each query. For that we have to do int A is at query, we will find A, B and C like this, right? And we have to compute the 3 distances A, B, B, C, AC, and we will compute subtree weight, right? So we will compute the subtree weight, and finally we'll store the result at the result output array, right? And once the result output array is built, right, then we will return the result. So this result array we are returning because it is containing the minimum subtree weight of each query, right? So as you can see, we have gone through this step, right? And to process pre-processing, right, O of n logs, it will take, because we are doing a lot of thing here, right? So so pre-processing will take you can say this DFS will take O of n into log n, right? And because we are taking, and because per query as you can see, right, for per query we are going for the, we are calculating the distance, right? And we are doing this, right? So per query will take O of n log time, and the space will take O of n log n for the binary lifting, right? So let me know if you have any doubt in this video, and I hope you will enjoy this video, guys. And if you have any doubt, please ping me in the comment box and let me know in the comment if you want to write this code, you want this code or anything. So if you found this video helpful, please smash the like button and subscribe for more advanced DSA breakdown. Okay, thank you for watching this video.